The electromagnetic force is responsible for the entirety of chemical phenomena. That positively charged protons and negatively charged electrons are attracted to one another is the reason that atoms form, the reason that chemical bonds and therefore molecules form, the reason that those chemical bonds have differing polarities, which lead to differing reactivities, as well as a method for enzyme recognition of substrate and DNA base pairing, which leads to life itself. But there are three other fundamental forces in the universe. The four forces are as follows. There's gravity, which is the weakest, but it operates on astronomical distances. So when you're looking at planets and stars and galaxies, this is the only force that matters. Electromagnetism, as we mentioned, is what makes chemistry happen, and it operates on the scale of atoms and molecules. But the other two forces operate on a scale even smaller than that, the scale of the atomic nucleus. These are called the strong nuclear force and the weak nuclear force. The strong nuclear force is what keeps the nucleus together, preventing positively charged protons from pushing each other away and splitting up the nucleus. And the weak nuclear force is what facilitates nuclear decay. These are instances in which the nucleus of an atom changes in some way. They are called nuclear processes, and though they are more in the realm of physics, they are important for chemistry because they often cause transmutation of elements. That's when an atom will change from one element to another. So we need to know a bit about them. To reiterate, in a chemical reaction, only the valence electrons of atoms are rearranging when chemical bonds break and form. The identity of each individual atom remains unchanged. In a nuclear reaction, changes occur to the fundamental particles in the nucleus of an individual atom, which means it will change from one element to another. These reactions are some kind of nuclear decay, where something in the nucleus disintegrates, giving off some form of radiation in the process. Radioactivity was first discovered by Henry Becquerel in 1896. He noticed that photographic plates had bright spots when they were exposed to uranium minerals. This radiation was found to be composed of three types when exposed to a magnetic field, since they were deflected in different manners. At the time, we didn't know about the subatomic particles the radiation was comprised of, so we just named them with Greek letters and discovered their identities later. An alpha particle is essentially a helium nucleus, 2 protons and 2 neutrons. In transmission, seen here. A beta particle is an electron. A positron is the antimatter particle of the electron, which has the same mass as the electron, but a positive charge. And a gamma particle is a photon of light. This is the same as the electromagnetic radiation from the Bohr model, just no longer associated with the transition of an electron. Let's quickly learn the ways that we can notate these particles so that we can write nuclear reactions. Remember that when we write nuclide symbols, the lower number is atomic number, or number of protons, and the upper number is atomic mass, or the protons plus neutrons. So a proton and neutron will be signified this way with a P and an N, each with mass 1, but only the proton has atomic number 1. An alpha particle can be represented as helium or with the alpha symbol. An electron can be either an E or a beta symbol, and the atomic number will be -1, while the mass, though technically not 0, is negligible, so we call it 0. A positron will be the same, but with a +1 here. And a photon will be gamma, both numbers 0, as it legitimately has 0 mass. So if we want to describe the emission of, say, an alpha particle, we would write it this way. Show the first particle, the arrow signifies a reaction, and then show the alpha particle. To figure out the resulting nucleus after emission, we just do some arithmetic, because the atomic numbers and mass numbers have to add up to the same number on both sides, kind of like how we need the same number of atoms on both sides of a chemical equation. If the atomic number is 86 on the left, and there's a 2 on the right, we need 84 for it to work out. Again, with mass, 222 on the left, 4 on the right, we need the other particle to be 218. Any atom with 84 protons is polonium, so the resulting nuclide symbol must be this. Again, the numbers on each side of the arrow add up to the same thing. Now that we are aware of these processes, why do they occur? It's always due to some instability in the nucleus. One reason might be that the nucleus is just too large. You see, the strong nuclear force, which is mediated by particles called mesons, is very strong, and it keeps the protons and neutrons fused together with 100 times greater force than the electromagnetic repulsion that wants to push the protons apart. But the strong nuclear force drops off with distance more quickly than the electromagnetic. So if the nucleus gets too big, all of a sudden the strong nuclear force is too weak over the diameter of the nucleus to keep it all together, and the protons will push apart. So for atoms larger than bismuth, the nucleus is just too big to be stable. Nuclei like these will often rapidly emit an alpha particle to try to get a little smaller and a little more stable. But even if the nucleus isn't too large, it may have a number of protons or neutrons that isn't ideal. The shell model of the nucleus describes nucleons as existing in levels or shells, kind of the way electrons do. As it happens, there are so-called magic numbers for each nucleon that correspond to a special type of stability, kind of like a full valence shell of electrons. These are the magic numbers. In addition, most stable isotopes of a given element have even numbers of both protons and neutrons, and most of the rest have at least one of them in even numbers. And lastly, an atom will tend to want a certain neutron to proton ratio in the nucleus. For smaller atoms, this is roughly 1:1, which is represented by this line. But for larger atoms, this becomes closer to 1.5:1, so more neutrons than protons. This ratio gives a nucleus balance, so if an atom veers too much in one way or the other, nuclear decay will allow it to adjust the ratio. So as we said, if a nucleus is too large, it will emit an alpha particle, or it can undergo spontaneous fission, where it breaks into multiple lighter nuclei and usually a few neutrons. In beta emission, the reason an electron is emitted is because a neutron spontaneously transforms into a proton. Remember before how we said that protons and neutrons both weigh 1 atomic mass unit, even though technically the neutron is slightly heavier. Well, it is heavier by exactly the mass of the electron, which is why a neutron is neutral. It's a proton and an electron combined. So when the neutron becomes a proton, it will emit an electron in the process. A nucleus would do this if the neutron to proton ratio was too high, meaning too many neutrons, as this would adjust that ratio favorably. Positron emission is just the opposite, when a proton becomes a neutron. This will emit a positron because this is the process that is the opposite of beta emission, and a positron is the opposite of an electron. This would happen if the neutron to proton ratio was too low, meaning too many protons. With both of these types of decay, there is also a tiny particle called a neutrino that is emitted. In beta emission, it's an antineutrino, and with positron emission, it's a regular neutrino. More on that in particle physics. Another process that can occur is electron capture. This is similar to positron emission in that a proton becomes a neutron, but it does so by absorbing an electron rather than emitting a positron. Once again, a proton plus an electron makes a neutron. The electron in question will tend to come from one of the inner orbitals of the atom, and the electron will be a reactant since it is absorbed by the proton to give a new particle. And lastly, if a nucleus is in an excited state, it can emit a high-energy gamma photon. In this process, there is no transmutation because we don't change around any protons or neutrons. So we can predict what kind of nuclear decay a nucleus might undergo by looking at its condition. Is it too large? What's the proton to neutron ratio? Each decay process has its typical cause. Too many protons, positron emission or electron capture. Too many neutrons, beta emission. Too big, alpha emission or spontaneous fission. Excited, gamma emission. An unstable atom can undergo a radioactive decay series that over multiple emissions generates a stable nucleus, like uranium-238, which eventually becomes lead-206. So now we know what radiation is. It's unstable nuclei emitting high-energy particles. The reason this is bad for biological organisms is that these high-energy particles can tear through our cells, and if one strikes a DNA molecule, it can potentially change the genetic code at that location, resulting in a potentially harmful mutation. Most elements have naturally occurring isotopes that do decay over time, even carbon, hydrogen, and oxygen. So there are radioactive nuclei decaying all over your body every second. Luckily, we have enzymes that repair DNA damage as it happens. But if we were to be in the presence of a highly radioactive substance that is emitting particles at a high frequency, this would do much more damage than our bodies can repair. So we have ways of detecting radiation like Geiger counters. We will often talk about radioactive material in terms of a half-life. This is the time it takes for a material to be depleted to half the original amount. After 2 half-lives, there would be 1/4 the original amount. After 3 half-lives, 1/8, etc. Half-life is given by the following formula, where K is a constant specific to the material. By learning about nuclear processes, we can harness the massive energy they contain. With nuclear processes, matter is converted directly into energy, as is given by Einstein's famous equation, E=mc². Here, c is the speed of light, which is very big. So what this equation says is that matter is simply extremely dense energy, the densest form there is. We have harnessed this power already with atomic bombs, much to the dismay of mankind. These worked by bombarding unstable uranium nuclei with neutrons, which cause them to split, generating more neutrons, which collide with other uranium nuclei, causing a chain reaction that releases tremendous energy. An even more powerful process is nuclear fusion. This is where small nuclei combine to give larger ones, a process that involves a loss of mass, which is converted into even more energy than a fission reaction. Reactors that harness the power of fusion promise to solve all kinds of problems regarding renewable energy sources, and could be the key to the next step in societal advancement. Maybe you can aid in the advancement of this or other important technologies. Let's check comprehension.
Okay, the 4 problems that Professor Dave has put up as his examples, they're good ones. And would you like to handle the first one? And so we're just going to transpose it to this platform here. Okay, so you get to fill out you get to complete this nuclear reaction and balance it.
I give you one of the most misshapen R's out there.
Okay, let's see, argon 18. Well, that's not what I got.
Okay.
So 18 plus 19, 42. It's a positron emission. So I got CA. Okay, no, you're correct based on what I gave you. If I put a -1 here, then
Oh, that would have been calcium.
Okay, good. So you get the concept. Essentially, you're doing okay. What is the name of this number that occurs in the in the subscript? What do you call this?
I want the atomic number. I'm gonna feel silly if it's something else.
Okay, good. So this is the atomic number, and which is the same as the number of protons. And then what is this number in the superscript? What is this referred to?
I'm not positive, but I believe it's the mass of the element.
Okay, that's the mass number. And the mass number, we usually refer to it as A, which is equal to the proton plus neutron. So, okay, you got it. Now, did you get the Microsoft Word document that I emailed to you, about half an hour ago?
I will tell you in about 5 seconds.
Okay.
Unfortunately, no.
Okay, you didn't get the document, huh?
But I do see something about the workshop number 9. Oh wait, no, that one.
Yes, yes. Okay, so let me go like this. I'm sharing my screen. Can you see these problems?
Not yet.
Not yet. Okay. Let me go share screen. Share.
I can see your screens.
Okay, so can you see the Microsoft Word document, nuclear chemistry?
Yes, I can. I can now.
Okay, great. So now here's problem number 1. I'm going to copy it and then bring it to the blank whiteboard. Okay, can you please pack this problem? Which element undergoes alpha decay to form lead?
When we were going over the video, I remember him pointing out uranium, but I didn't understand exactly why.
Okay. Can you write in the form of a nuclear reaction what we know and what we don't know? So just kind of formulate a balanced nuclear reaction with what we know and what we need to figure out.
All right, sure.
Okay, so basically what I would actually do here is recognize, it says what element undergoes alpha decay. So what that tells me, and it says to form lead-208. So if it undergoes alpha decay, that means one of my products is an alpha particle. Otherwise,
Oh my goodness, I put the, I'm sorry, put the electrons on the wrong side.
And also, there's no electrons here either. Because alpha decay isn't an electron, alpha is a helium nucleus.
Oh, thank you.
No problem. And this is to form lead-208. Well, I know that the symbol for lead is Pb, as do you, because you put that down. And the 208 is the mass, so that's the number on the top. And I also know from looking at the periodic table that the atomic number is 82. So now what I have to recognize is that the nucleus that I started with here has to basically contain the same total mass and the same total charge as the two particles here together. So what that means is to get the total mass, I'm just going to have to add 208 to 204, or 204 rather, 28 to 4, and that's going to give me 212. That'll be the total mass of this nucleus, this original nucleus. And the total charge, well, there's a 2 and an 82, so the total charge on this side must have been 84. And so based on the fact that it's atomic number of 84, what element might this be?
Polonium.
Polonium, yep. Ta-da!
Okay, this works. This second equation works. And then one of the things that Professor Dave talked about is, how do we know which elements are radioactive and which are not? And we don't have any laws. We don't have any laws really, but we just have some guidelines. So what do you see that is special about polonium, or about this number 84?
I'm gonna feel silly when you tell me, because I'm goodness, I'm missing something that silly.
No, it's fine, but just again, there's no law. It's just kind of a guideline. This any element after bismuth, and bismuth has atomic number 83. So any element after bismuth is going to have a unstable nucleus, which means it's going to be radioactive. And this polonium is really 84 is the first element following bismuth that just based on the atomic number, and we don't have to do any evaluation with the proton to neutron ratios, and we just know that this is the first element in the periodic table that is radioactive.
So bismuth is not necessarily radioactive, but polonium is. We start at 84, and
Yeah.
nuclear forces are more powerful than the strong nuclear forces.
Yes, I mean remember the strong nuclear forces start to disintegrate just when the nucleus becomes very large, so it doesn't hold up very well. So it's when processes, these nuclear processes start to occur, and so polonium is really one of the first ones. It follows bismuth, and it's got an unstable nuclei. The strong nuclear forces are starting to fail, and then in order to become stable, then it does alpha emission. Okay, please do this one. We want a balanced nuclear equation for the reaction in which oxygen 15 undergoes positron emission.
Did I miss something obvious there?
Whale. Okay, so one thing to keep in mind is when we have these nuclear types of decays, we are not going to end up with the same atom.
Are we coming into carbon in this case, or?
Let's see. So your your positron is correct. Your positron, this is correct. Oh, actually, is it? It's, okay, so here's where we messed it up. With the positron, let's not write it like that. And this just takes practice to get used to writing them correctly. Let's see, it's going to be, oh. So let's go, 15, 8 goes to E0, 1 plus, now I think we can better find the answer.
I have a feeling we're going for a nitrogen 14.
Yeah,
Based on
well,
the,
yeah, I mean, okay, so your 7 is correct. Your 7 is correct. This in the subscript, the 7 is correct. So then which one is going to be the atom?
I believe nitrogen.
Okay, so that, and then what's the mass number going to be?
I thought 14, but I have a feeling I'm missing something.
Okay, so let's see. 1 plus 7 is equal to 8, and then something plus 0 is equal to 15.
Oh, 15.
Okay. Okay, so we did this one. Yay.
Okay.
Now let's go to let me go to share, and can you see problem number 3? Is this visible?
Yes, with a little bit of strain, but yes.
Oh, okay. So it is asking which of the following nuclides would you expect to be radioactive? Nickel 62, copper 58, silver 108, tungsten 184, and polonium 206.
I believe only the polonium, 84.
Yes, you are good. You are good. You nailed it.
Thank you.
If you were to evaluate it more systematically, for example, if the atomic, if the proton number, if the subscript, the atomic number wasn't so clear, then what would you have done?
I'm not sure if I missed something, but I would divide the atomic mass by the atomic number and find the average mass.
Okay, so if you mean that you're going to look at the neutron to proton ratio, then you're on the right track. And then with the neutron to proton ratio, there's that up till 1.5, the ratio of 1.5, it works pretty well. But if it's above that belt of stability, then it does, it does the radioactive decay. And then if it's below that belt of stability, again, it does a radioactive decay to become stable. So this is something that Professor Dave talked about, and just again, it's a guideline. So just keep in mind that you're looking at neutron to proton ratios in order to evaluate which nuclei are radioactive or not. Michael DePaul, do you have anything to add here?
I don't think so.
Okay, very good. So we will go to the next one. So I'm going to copy and paste the nuclear reaction, and you're going to balance it and complete it. Can you tell us how you would complete and balance this nuclear reaction with the californium-252 and the boron-10, which does a neutron emission? But notice that here it's a little bit tricky because there is 3 neutrons that have been emitted. So I'm going to, let's see, I'm going to try to make you moderator so that you can write on this screen. Let me see how to do that.
For what it's worth, the screen hasn't popped up right now.
Oh, the screen hasn't popped up. Let me try again. So basically, we are looking at problem number 4, and I believe you should be able to write on this page now. So just one thing to remember is that it's a little bit tricky because it's not 1 neutron that it's emitted, it's 3 neutrons. So how would you handle this problem?
Well, bear with me, I'm running in zombie mode right now. Pardon me.
No problem. Would you agree that okay, so on the left hand side we have 98 plus 5, which is equal to 113.
Yes, that part makes sense so far, but I'm
Okay,
missing
so
something else.
okay, very good. So the atomic number, we have 113 on the right, and no, on the left hand side. On the right hand side, 3 times 0 is 0. So what should go on the atomic number in the subscript of that element?
I believe we're just going to add the subscripts and make it 103.
Or you mean 113, right?
I do know. I'm missing something.
Okay, so let me say insert equation.
Shoot.
113 down here. And then goes up here in the subscript. I mean in the superscript.
I'm going to guess right now 259.
Okay, excellent. 259. And then when we go in the periodic table, depending on how old it is, this 113 might be empty, or some of the newer ones have identified it as a very unstable radioactive element. I can't remember the name. We'll just call it X. But you get the idea. You did the balancing correctly, and there you go. And now let's go and do this one here. 3. So let me go insert equation like that. Okay, so what goes on the bottom?
I believe your subscript is going to be 0. No, I was thinking with an effective mass of 0, but I'm thinking about the.
Yeah, that's not going to fly, because one and the proton numbers 1 plus 5 is equal to 6. So we need what do we need to make it, because there's 3 moles of it. What do we need in order to make?
Oh, 2. So we're gonna have helium. Okay.
Perfect. So then what goes on in the mass number?
Let's see. 12 divided by 3 gives me 4.
Okay, wonderful. So then 2 we know is helium. So this is the alpha particle. Yay, we did it.
Thank you.
We are moving fast. Let's go to the next problem. Yeah, we can do it here. Okay, so they tell us the half-life of a radioactive element, cobalt-60, is 5.3 years. How much of a 1 milligram sample of cobalt-60 is left after a 15.9 year period? How do I attack this problem?
I remember something about exponents. I'm trying to remember the exact one.
Yeah, so we just have to remember the definition of half-life, and half-life is the time that it takes for the amount of the radioactive element to subside to half of it. So if we know the half-life is 5.3 years and the interest is for 15.9 years, 15.9 divided by 5.3 is 3. So three. Basically, we want to know how much is left after 3 cycles, 3 half-life cycles. In the first half-life cycle, 1 milligram, so after 5.3 years, 1 milligrams goes to half of it, which is 0.5 grams.
And then 0.25 and then 0.125.
Yay.
So 1/8 milligram.
Yay.
Thank you.
Excellent. Okay. 3. Okay, so now we have a problem where um, we start with 1 gram of strontium-90 and 0.953 grams will remain after 2 years. So we need to calculate the half-life of strontium-90. We just have to remember that the half-life of nuclear decay follows first-order kinetics. So in first-order kinetics, there's a relationship that we remember. Let me see what's the best way to do this. Let me take this problem to the other screen. Copy. You sound like you are sleep deprived.
Just a touch, honestly. There are people who have it a lot worse.
Well, you're doing well.
Thank you.
Okay, so Michael Depot, can I get your assistance? This is very hard for me to write on the screen. Can you write for me the relationship for the first order kinetics that relates the rate constant to the half-life? Let me see. Hold on. Let me see if I can find that stylus pen. It might help a little bit. Start. Okay. This is going to look pretty bad, but
I will give you exactly 0 seconds of grief.
right. Okay, pen. Okay, is equal to 0.693 over T1 half. Do you remember this from first order kinetics, the relationship between the rate constant and half-life?
At the present time, I barely even remember my name.
You're so funny. Okay.
With the giggling, I think you may be sleep deprived too right now.
Yes, I definitely understand it. Currently, I'm not sleep deprived, but I've gone through many rounds of sleep deprivation. So yes, I know. Okay, so this we just have to remember it. So I'm just going to ask you to remember that and refresh your memory. And then also, I'm also going to ask you to remember this relationship here, natural log of, natural log of n over n naught is equal to minus kt. So let's just say we remember these relationships and we're going to reapply what we remember from first order kinetics to nuclear decay. So now I'm going to see what the problem gives me. The problem gives me the original amount of strontium, and then so the problem gives me n naught. The problem also gives me n 0.953 grams will remain after 2 years. So I also have t. So if I have n naught, and t, then I should be able to find k. So let me go and set this up like this. Hold up. So let's see. natural log of 0.953 grams over 1.00 grams is equal to minus K times 2 years. And then if I take my calculator and take the natural log of 0.953, I get minus 0.048 is equal to minus K times 2 years. And I'm going to erase this so that I can have room to write. Are you okay with it? Hello?
I'm here. So far, I'm up to K being 0.024.
Oh, good job. Good job. Excellent. So you got K is equal to 0.024 and the unit is per year. Excellent. K is equal to 0.024 and the unit is year inverse. Excellent. So now, let me erase. So now we can go and plug and chuck in our original equation. T1 half is equal to 0.693 over 0.024 year inverse, which is equal to
And I got 28.8.
excellent, 28.8 years. Excellent. We nailed it.
Thank you.
Now, the second part of the problem, the second part is asking to find the amount of the nuclide that is left after 5 years. So you should have the, if I go back and forth, it takes a long time, but I'm going to stick on this page. And I sent you the Microsoft Word document. If you don't find it, I can resend it to you. But essentially now we have to go back to the natural log of n over nt, it's or n0, which is 1 gram, which is equal to minus kt. We determined k to be 0.24 per year minus inverse times 5 years is equal to, or we can say natural log of n is equal to minus 0.120, or n is equal to e to the minus 0.120, which is equal to 0.887 grams.
C to the perfect.
Okay, excellent. You're doing very good. We just have one more problem to go, so just bear in there with me. Okay, so this is the last problem. Let me see how to, hold on 1 second. So 1412 workshop, share, and then can you see this problem? Find the energy associated with a nuclear reaction giving the following masses.
Yes.
Okay, great. So um, um, first I'm just going to describe to you what we're going to do, and then we'll attack it. So with a nuclear reaction, the energy associated with a nuclear reaction follows Einstein's relationship, E is equal to mc squared. The only thing that we have to be cognizant of in this reaction is that we're dealing with really the change of energy, and essentially the relationship becomes delta E is equal to c squared times delta m. So once we find delta m, then we can plug and chug into the famous E is equal to delta m c squared equation, and we're good to go. And delta m is determined by the masses are given. So it's going to be the atomic masses of the products minus the atomic masses of the reactants. And if we assume just 1 mole, we can just convert the AMUs to grams. So based on that, let me go to the white blackboard and calculate delta M. Delta M is equal to
We had 238.0003 for the uranium.
actually, so it's going to be products minus reactants. So it's going to be 233.9942 plus 4.0015 minus 238.0003, which is equal to minus 0.0046 grams, and this is for the decay of 1 mole. If we assume 1 mole, then we can go from AMUs to grams. And then we can just go straight to E is equal to delta M C squared, which is equal to C squared times delta M, which is equal to
Do you use 2.99 times 10 to the 8th, 3.00 times 10 to the 8th, or another figure now?
okay, so you're excellent, except we use for such purposes we use 5 significant digits. So I'm going to use 2.9979 times 10 to the 8th meters per second squared times minus 0.0046 grams, and then we're going to multiply it. We're going to convert it to kilograms. So we're going to go use the conversion factor 1 kilograms over 1,000 grams, which is equal to minus 4.1 times.
negative 0.000046. All right, so I got negative 4.13 times 10 to the negative, times 10 to the 11. Assuming a mass of 4.6 times 10 to the negative 5 and constant for C of 2.997, actually 79 times 10 to the 8th, and squaring that. I appreciate y'all's patience and sense of humor so much today. I am going to be a little selfish and run away now, but thank you so much.
Okay, excellent. Good job.
But was that the answer though?
Yes, my microphone cut off, but I was telling you that the answer is minus, like you said, and then the units kilogram meter squared per second squared, which is joules. So your final answer is minus 4.1 times 10 to the 11 joules, which means that it was a spontaneous reaction because of the negative sign. It was a spontaneous reaction, but excellent. I mean, I think you got it. You nailed it.
Spontaneous reaction because I was just only thinking about exothermic because of the negative sign.
Yes,
But,
and yes, you're correct. In fact, you can say it's exothermic. We just don't use that word when we're doing nuclear reactions, but in a sense, yes, it's releasing a ton of energy. Yes, you're on the right track.
Thank you again so much for your time, and I hope you guys have a good one. I will listen to anything else y'all record later, but thank you so much.
Okay, excellent. Well, you take care. Good night.
Good night.
Okay.